Welcome back to Basic Electronics. In this lecture, we will continue with the half-wave rectifier example from the previous class. We will estimate the maximum current that flows through the diode and also obtain an analytic expression for that current. We will then repeat the calculations, that is ripple voltage, average and peak diode currents for a full wave rectifier circuit. Finally, we will compare the half wave and full wave rectifier circuits with respect to different criteria. So let us get started. Let us now talk about the peak diode current, and to begin with, let us remind ourselves of what ID looks like as a function of time. This plot here, ID is non-zero only in this short interval marked as TC here, and otherwise it is 0. Alright, now what is ID given by? ID is given by IC plus IR. IR is more or less a constant because VO is constant, approximately equal to VM. So therefore IR is VM by R, and that is already known. What we need to now worry about is this capacitor current. And in particular, we need to worry about IC in the charging interval, this interval here, because that is when this diode is conducting. Now when the diode is conducting, this voltage is 0, and therefore VC is the same as Vs. So therefore the capacitor current IC, which is C dVc dt, is the same as C dVs dt. And the diode current is maximum when IC is maximum, because this current here is a constant. So we need to now answer two questions. One, when is this derivative dVs dt maximum? Because C times that derivative is going to give us the maximum capacitor current and therefore the maximum diode current. And second, what is the value of that derivative? And to answer those questions, let us once again look at the interval in which the capacitor is getting charged. That is when the diode is conducting. That is this interval here. And we are interested in finding the maximum value of dVs dt in this interval. So this is how Vs varies. And clearly the maximum slope happens at this point right here, and that is t equal to minus Tc. This is our t equal to 0, so this is t equal to minus Tc. So what we need to do now is to find the slope dVs dt at this t equal to minus Tc. So that is the equation for the peak diode current, C dVs dt evaluated at t equal to minus Tc plus the resistor current IR, which is approximately constant Vm by R. Vs is Vm cos omega t, and that is because we have taken our time equal to 0 at this point here. So when we differentiate, we get this result. This 0.16 is coming from IR, Vm by R, and the first term, the capacitor current, is omega times C times Vm sine omega Tc. Now in this expression we know everything, omega C Vm except Tc. So Tc is something that we need to figure out, and let us see how that can be done approximately, and that is from this equation. So what can we say about the value of VO at this point t equal to minus Tc? That is nothing but Vm minus Vr, because the difference between these two is Vr, and therefore at t equal to minus Tc, VO is Vm minus Vr, and so we can use that condition to get Vm cos of minus omega Tc equal to Vm minus Vr, and that gives us an idea of what Tc should be. So omega Tc then is cos inverse of 1 minus Vr by Vm. Vr is 2 volts, Vm is 16 volts, and omega Tc then turns out to be 29 degrees. When you use your calculator to compute this omega Tc, you need to be a little careful, because your calculator may give this value in radians, and then you need to convert that into degrees, or you can keep it in radians but then be aware that it is in radians. Okay, now we have got omega Tc. Now it's a simple matter of substituting omega Tc here, and this current then can be evaluated like that. So this is the peak diode current. The first part here is 2 pi times f, or omega. F is 50 hertz. C is 1600 microfarads. We have already computed that earlier. Vm is 16 volts, then followed by sine of 29 degrees. That 29 degrees is coming from omega Tc. So all of this turns out to be 3.89. To that we have to add the resistor current, 0.16 ampere. So it's 3.89 plus 0.16, about 4 amperes. One important thing to note here is that the maximum capacitor current is much larger than the average resistor current, and that we can also see from this figure here. That is the maximum capacitor current, and this value here, the one which is going negative, is the average resistor current. Let us now obtain an analytic expression for the peak diode current. We begin with this condition: the source voltage at minus Tc is equal to Vm minus Vr at that point. We have seen that in the last slide, and that gave us an expression for cos omega Tc as 1 minus Vr by Vm. And earlier we calculated omega Tc using a calculator, got a numerical value for omega Tc, and then proceeded. Now we want to do the same thing analytically. So let's write Vr by Vm as x. What is x in this case? Vr is 2 volts, Vm is 16 volts, so x is 2 by 16 or 1 by 8. So x is small compared to 1, and we will use that. Alright, from cos omega Tc, we can write sin omega Tc as 1 minus cos squared omega Tc, square root of that. So that is 1 minus cos omega Tc is 1 minus x, so square of that. And now let's expand this. We get 1 minus 2x plus x squared. This one cancels with that one, and we get 2x, and there is a term in x squared. Our x is 1 by 8, so x squared is going to be 1 by 64, much smaller than x, and therefore we can ignore x squared compared to x. So we end up with square root of 2x. So that is square root of 2 times Vr by Vm. And now you can use this result to get the peak diode current. It's IR plus C dVs dt evaluated at t equal to minus Tc, and as we have seen in the last slide, this is the same as omega C Vm sin omega Tc, and the sin omega Tc can now come from this result, and that is what we get finally. What about the maximum reverse bias? We have already seen earlier that it is going to be 2 times Vm, where Vm is the peak value of the input voltage. Let us quickly go through that argument once again. Vd is equal to Vs minus Vo. Now Vo is nearly constant, that is equal to Vm. and therefore Vd is equal to Vs shifted down by Vm, because Vd is Vs minus Vo, and that essentially is this waveform here, and the lowest value is minus 2 Vm. So that means the maximum reverse bias is 2 Vm. In this case it is 32 volts. And we should keep in mind that all these calculations that we are doing are not simply academic curiosity. These numbers, that is the average diode current, the peak diode current, the maximum reverse bias, are very important in practice, because that will decide what diode we are going to pick over here, and consequently the cost of the circuit that we are going to build. Here is the SQL circuit file, so you can run the simulation and check whether you get all of these results given here. You can also change some of these component values. For example, you can make this capacitance double of what it is now, predict what the new ripple voltage is going to be, what is the new peak diode current, and so on, and then check with the simulation results whether your predictions are correct. In general, it is always good to at least have some idea of what to expect from your simulation, and not just run the simulation blindly and see what you get. Sometimes your predictions may not be correct, and that is even better, because then you will figure out what mistake you made, and chances are that you will not make the same mistake again. We now look at the full wave or bridge rectifier with a capacitor filter, and at this point it may be a good idea to go back a few slides and revise the case of full wave rectifier without a filter. What we will do now is make a few observations and then take up a numerical example. First, as in the half wave rectifier case, we have charging and discharging intervals, and VO is approximately maintained at Vm. So let's look at the waveforms. This is the input voltage Vs. That dashed curve is the negative of input voltage. Vs goes from plus Vm to minus Vm, and that is the output voltage, the one shown in the pink graph. And the output voltage is nearly constant, but there is a small ripple, the difference between the maximum and minimum output voltage levels. That's called VR. When the input voltage Vs goes beyond the output voltage, D1 and D2 conduct, and when minus Vs goes beyond the output voltage, D3 and D4 conduct. And once again, the diode currents will turn out to be large compared to the load current. So those points are listed here. The discharging interval is typically much longer than the charging intervals, TC1 and TC2. This is TC1 here, and in the TC1 interval, D1 and D2 conduct, and D3 and D4 are not conducting at that time. In the TC2 interval, D3 and D4 conduct, and D1 and D2 remain off. The maximum reverse bias across any of the diodes is Vm. Here is the diode voltage Vd1, and it's actually the same as Vd2, and we notice that it goes from 0 to minus Vm. So the maximum reverse bias across D1 or D2 is Vm. This one is VD3, the same as VD4, and once again the maximum reverse bias across D3 or D4 is Vm. Notice also that VD1 or VD2 is 0 when D1 and D2 conduct. Similarly, VD3 and VD4 are 0 when D3 and D4 conduct. So we observe that there are many similarities between the half wave rectifier and full wave rectifier with filter. The main difference is in the charging of the capacitor. In the half wave rectifier, there was only one charging interval. In the full wave rectifier, there are two charging intervals within one period. For example, if we go from t equal to 0 to t equal to t, this point here, then there is one interval in which charging takes place through ID3 and ID4, and another interval in which charging takes place through ID1 and ID2. Apart from that, things are very similar. There is a charging interval in which the output voltage, that is the capacitor voltage, follows the input voltage, and the charge on the capacitor gets replenished, and when the input voltage goes down, the charging stops, and now the capacitor discharges through the load resistor, like that. Here is a numerical example, and we have kept the numbers the same as the half wave rectifier circuit. The maximum voltage, input voltage, is Vm equal to 16 volts. Frequency is 50 Hz again. The resistance, load resistance is 100 ohms. And for the same ripple voltage of 2 volts, we want to find the filter capacitance, the average and peak diode currents, and the maximum reverse voltage appearing across each diode. Once again, we will assume the voltage drop across the diodes to be 0 volts when they conduct. Let's look at the filter capacitance first. When the diodes are not conducting, we have R and C, the capacitor discharging through the load resistor, and we are talking about this interval or this interval. In these intervals, the capacitance current is the same as the resistor current in magnitude. So IC is equal to IR, and since VO is nearly constant, we have IC equal to Vm by R. The capacitor current is given by C dV dt, and since this variation is once again linear, we can replace dV dt by delta VO by delta T. Delta VO is the same as ripple voltage here, and delta T is the duration of the discharge interval. So let's take this interval for example. So that is from t equal to 0 to this point here, which is nearly equal to t by 2. So we substitute for delta t, t by 2, and then we get VR equal to Vm t by 2 RC. And the capacitance is now Vm by Vr t by R divided by 2. This half is new here. It was not there in the half wave rectifier, and when we substitute all the numbers, we get 800 microfarads. What about the average diode current? Now, as we observed earlier, half of the charge lost by the capacitor is supplied by ID1 or ID2, because T1 and D2 conduct at the same time, and the other half is supplied by D3 and T4. that is this situation here. And therefore we can write the average diode current, let's say through D1, is 1 over T times half of the charge lost in one cycle. And the charge lost in one cycle is easy to calculate. It is simply the resistor current, the average current times the time period T. And so this T cancels and we end up with Vm by 2R. So that's 16 volts by 2 times 100 ohms, which is 80 milliamps. Let's look at the peak diode current, and let's say we are talking about ID1. So ID1 is maximum here, and as before, this is the sum of IC and IR, because the current, it's applying both the resistor and the capacitor. And the resistor current, of course, we already know it's approximately Vm by R, and the capacitance current, like in the half wave case, is the slope of this is given by the slope of this input voltage, and it is maximum at T equal to minus Tc1. So that is what we get, and the next step now is to find Tc1, and we do that following the same procedure that we used for the half wave rectifier. That is, we know that at this time, which is minus Tc1, the output voltage is Vm minus Vr, and therefore we can get omega Tc1 as cos inverse of 1 minus Vr by Vm, which turns out to be 29 degrees. So now we substitute this in the expression for ID peak. That is omega 2 pi times 50, C 800 microfarads, Vm 16, and sine of 29 degrees. That's omega Tc1. So all that is the capacitor current at minus Tc1. To that we add the resistor current 0.16 amp, and we get a total of 2.1 ampere. So that is the peak diode current for D1, and by symmetry it would be the same for all the diodes. Let us look at the maximum reverse bias that each diode comes across. Let's take D1 as an example. Here is VD1. When D1 and D2 conduct, of course VD1 is 0, and it goes through its maximum negative point when D3 and D4 conduct in this interval here. So let's look at the circuit when D3 and D4 conduct. This circuit, D3 is conducting, so no voltage drop there. D4 is conducting, so no voltage drop here. So the negative end of D1 is at node P, and the positive end is at the same potential as node Q. So the difference between P and Q, which is Vm, appears across D1, and that of course is a reverse bias because Vp is higher than Vq. So that's how we get the maximum reverse bias across D1. It happens to be Vm, and that is 16 volts. And that is true also for the other diodes. The SQL file for this circuit is available, and you can run the simulation. Let us now compare the half wave and full wave rectifiers with the capacitive filter for the same source voltage, that is same Vm, same load resistance R, and the same ripple voltage. And if you recall, in the numerical examples that we looked at, we did follow these conditions. That is, we kept Vm, R and Vr the same for the half wave example and the full wave example. So this table shows the comparison. Number of diodes, 1 in the half wave case, 4 in the full wave case. Filter capacitance, if this is C, then this is C by 2. Average diode current, if this is ID average, then this is ID average by 2. Peak diode current, if this is ID peak, then this is ID peak divided by 2. Maximum reverse voltage, in this case it was 2 times Vm. In the full wave case it was Vm. So although the full wave rectifier requires 4 diodes as opposed to 1 here, it requires a smaller capacitor, and also the diode specs are less stringent in the full wave case, and that is an advantage. To summarize, we have carried out calculation of ripple voltage, average diode current and peak diode current for the full wave rectifier. We then compared the half wave and full wave rectifier circuits with respect to different criteria and found that the full wave rectifier requires less stringent specifications for the components, namely the filter capacitor and the diodes. That is all for now. See you next time.